So vectors that have the same magnitude as well as the same direction and the same units are called as equal vectors. So let us say this is A vector. B vector represents the same quantity that A vector represents. Like for example, both represent force or both represent momentum, and B vector is equal in length compared to A vector and has the same direction as that of A vector. Then we say that A vector is equal to B vector. In any other case, equality between two vectors is not to be specified or not to be defined. Parallel vectors are vectors pointing in the same direction, and anti-parallel vectors are vectors pointing in exactly opposite directions. Collinear vectors are the vectors that point in the same direction as well as lie along the same line. Usually, vectors are free to move parallelly to themselves, but here in case of collinear vectors, we assume that collinear vectors are lying on the same line, so they are not necessarily free to move parallel to themselves. Let us say we have a vector p bar and we have a vector anti-parallel to p bar representing the same quantity and having the length equal to the length of p in magnitude, but the direction is opposite to that of p. Then p vector plus q vector is going to give us p vector plus effectively negative of p vector, because q vector happens to be exactly negative of p vector. So this is going to give us 0, but we'll have to write 0 with a vector arrow on top. So this is called as a null vector. Why? Because the left hand side of this equation happens to be a vector quantity, so the right hand side also has to be a vector quantity only. So null vector is defined as a vector with 0 magnitude and an unspecified direction. Because it has magnitude 0, we can't really point the vector in any particular one direction, or we can't really say that this vector is pointing in this particular direction. Unit vectors are obtained by dividing a given vector with its own magnitude. So the magnitude of a vector is represented with vertical parentheses or vertical lines like a mod sign enclosing the vector symbol. So this is also represented like this: a bar divided by a. Only the letter a also represents the magnitude of vector a. So when we divide the vector a by its own magnitude, we get a unit vector in the direction of vector a. Unit vector is a vector having magnitude of 1 unit and the direction that is specified as the direction of a. Like for example, this is a vector, then a cap, small a cap, lowercase a cap is the vector that points in the direction of a vector and has the magnitude of 1 unit. So in our literature, orthogonal unit vectors are defined along the x, y and z axis. Okay, so these are the orthogonal unit vectors: I cap, j cap and k cap. So I cap is the unit vector that points along the x direction. So this is, let's say, the x axis. This is, let us say, the y axis. Let us say this is the z axis or the z axis. I cap is a unit vector that points in the direction of the positive x axis. That's I cap. So j cap is the unit vector that points in the direction of the positive y axis, and k cap is the unit vector that points in the direction of the positive z axis. Coplanar vectors. So if any two vectors are free to move, they are always coplanar. Coplanar vectors are essentially, as the name suggests, vectors that lie in a plane. So vectors that lie in a plane are coplanar vectors. So let us say, even if the vectors were not to lie in a plane, as long as two vectors are there and they are free to move, we can always adjust them in such a manner that both of them define a plane. However, if they are not free to move, then it may so happen that one vector is lying in this particular plane and another vector is lying in another plane that plane which is not the same as the plane of the first vector. Also, we can draw more than two vectors that are non-coplanar. Like for example, these vectors that are not lying in each other's plane are non-coplanar vectors. So the third vector here, as we can see, is out of the plane that is defined or specified by the first two vectors. So coplanar vectors are the ones that lie in a plane, and two vectors that are always free to move can always be so adjusted that they lie in a plane. So two vectors that are free to move are always coplanar. Non-coplanar vectors are the ones that cannot be fit into any particular given plane, so they are non-coplanar vectors. Polar vectors are vectors that have a specified point of application. Like for example, let us say this is an object that is a three-dimensional object. So applying a force to this object at this point is not going to be the same as applying the force to this object at this point. Is not going to be the same as if I apply the force at this point. So basically the force that is going to be applied has to be applied at a specific point in order to get that specific response of specific mechanical response of that particular object, and hence the point of application of the force has to be specified. Such vectors are called as polar vectors. Similarly, let us say this is a point A and this is a point B. Let us say the path of the particle from A to B as it moves from A to B is like this, but the displacement vector always has to point from the point A to point B. So point A and B are locally fixed in space. That's why the displacement vector also has to be fixed in space. So if we do represent this on the axis, let us say this is the point A and this is the point B. So the displacement vector, so these are the position vectors defining the position of the point A and position of the point B. So the displacement vector as the particle goes from point A to point B via whatever path is given as this vector. So this displacement vector S bar happens to be a polar vector, wherein the point at which the polar vector starts or ends is completely specified. So even if the starting point is specified, since the direction and magnitude of the vector is known, the ending point automatically gets specified. So polar vectors are the vectors for which the point of application has to be specified. They are not free to move parallelly to themselves as compared to a general vector that is free to move parallelly to itself. Now axial vectors, sometimes we get quantities that are pointing towards the axis. Like for example, a particle that is undergoing circular motion. So there is this quantity omega bar defined that is along the axis. So this omega bar, or the angular velocity of the particle, is defined as per the right hand thumb rule. So if we wrap the fingers of our right hand, then the direction of the thumb is going to tell us the direction. So these are the fingers of our right hand. Let us say if we wrap the fingers of our right hand along the circumference, then the direction of the thumb is going to tell us the direction of omega. So this is called as the right hand thumb rule. So omega points along the axis of rotation over here. So since it is pointing along the axis of rotation, this omega vector is called as an axial vector. Later in this analysis of scalars and vectors, we are also going to learn about the cross product between two vectors. So the cross product between two vectors A and B also happens to be an axial vector. So let us say this is the plane in which two vectors, vector A and vector B, are lying. Then the cross product of vector A and vector B happens to be a vector that is perpendicular to the plane along the axial direction. So this vector A cross B can also be said to be an axial vector.